Howdy, calculus nerds. In this video, we're going to look at some special graphs. We're going to look at two new parent functions, two that you might not have seen in previous courses that are kind of important to us when we begin to study limits. All right, so that's our objective. Let's look at two new parent functions and transformations on those parent functions. It says sketch a graph of each function by completing the table of values, which we will do. But before we do that, I want you guys to put y equals 1 divided by x squared into your calculator and see what the graph looks like. So pause the video, enter this equation, hit probably zoom 6 for a standard viewing window. That's a good window for this graph. All right. You're going to see something like this. Some might say this is togetherness near the positive y-axis. This is what the graph looks like. So let's see if our table of values support this graph right here. So sketch a graph. Now we're going to do by hand and see if these values make sense with this graph. Sketch a graph of each function by completing tables of values. We're actually just going to do it for this first one, and then based on what we see, we won't have to create a table of values for these additional examples because we'll find some patterns. All right, this is our independent column. We'll label it X. This is our dependent column. We'll label it Y because we have X and Y. We're going to use some common integers, -3 to +3. All right, so let's generate the output value. So plug in -3, square it, we're going to get 1/9. Evaluated x equals -2, that becomes 4 in the denominator, so we have 1/4, etc. What happens when you put in 0? Well, you divide by 0, which is a bad thing. You get 1/0, and we call that undefined. That means there'll be no point on the graph when x equals 0. And real quickly, you can see when x is 0, you look up, you look down, there's no point on that graph. This graph is discontinuous at x equals 0. There's a break in the graph, as suggested by this vertical asymptote at x equals 0. Plug in 1, you're going to get 1. Plug in 2, you're going to get a 4th, and then you're going to get a 9th. And the reason, of course, you have all positive values here except for at x equals 0 is because you have a square on the input value in the denominator. All right, let's see if we can go ahead and locate these points. So I don't know, I'm just going to, my graph might be off a little bit because I sketched it first, but -3, -2, 1, 0, etc. 1, 2, and 3. Coming back over here to the ordered pairs, -3, so this must be -3, +1/9. Whoop. -2, +1/4. So we're increasing, but not very much, because 1/4 is a little bit bigger than 1/9. And we'll say -1, 1. Okay, then we've got 1, 1, etc. And then we've got 3, 1/9. All right, so the parent function that we're looking at that we want to memorize is this one right here, where you might say you have togetherness coming near the positive y-axis, and the graph just zooms upward. Some other features we might be interested in: what's the domain and what's the range? Well, the domain would be all real numbers except for x equals 0. So no matter what happens here, no matter how many more input values I put here, as long as I don't use x equals 0 again, okay, I can put any number in for x and square it except for 0. So all real numbers but 0 would be part of my domain. This is interval notation, which means I come up from -infinity to 0, but we don't want to include 0. You can use a comma or a union. And then my domain continues on the other side of x equals 0 to +infinity. All right, what about the range? Well, we kind of come up here. It doesn't appear that I'm ever going to reach 0 either on this branch or this branch. I'll never get 0 as an answer, because the only way to get 0 as an answer is if the numerator is 0. So to me, it looks like my domain, or excuse me, my range is going to be 0, but not including 0. And then I can have all real numbers up to infinity. All right. Let's look at some other notation too. What about this? What if you were just presented with, what is f of -3? What's f of +2? And what's f of 0? We're studying a new parent function, but I wanted to revisit domain and range, and I also want to revisit function notation. I hope you see that f evaluated at -3 can just be extracted from the table, or you can just go ahead and plug in -3 for x again, and you're going to get 1/9. So this function notation represents the ordered pair -3, +1/9 on the graph. F of 2, we already have it, is 1/4. So the ordered pair that's represented by this function notation is 2, 1/4, which is what we graphed. F of 0, well, there is no output value. There is no y when x is 0, so we just call this undefined. Some would say does not exist. Both are acceptable. So study your parent function, look at it, look at the equation that determines that parent function. Now let's look at some transformations. So let's look at A. If you had to guess, okay, what transformation is occurring to the parent function based on the change that we have in this new equation? Some might say that I need to move the graph right 3. Some might say left 3. Some might say, oh, I think you have to move it up 3. Some might even say you have to move that graph down 3 of the parent function. Well, we have a quantity, x minus 3. The -3 or the 3 is inside with x, as opposed to outside, which we'll see in just a bit. So this is actually a horizontal shift, not to the left in the negative direction, but to the right. So can we take this graph, okay, and shift it right 3 and get a new graph for this function as opposed to creating a table of values like we did up here for this graph? I don't want to do a table of values. That's too much work. So for me, I'm going, yeah, I think I'm just going to shift that graph of the parent function right 3. So what would be a key feature to shift right 3? Well, notice that you have a vertical asymptote at x equals 0. So how about if we shift that vertical asymptote to the right 3? So let's just document it, 1, 2, 3. Let's put in a vertical asymptote here. And then from there, we can just have togetherness around x equals 3 and draw the same basic shape of the parent function. So what's the domain here? Is it the same as the parent function? What about the range? Same, or are there some changes? Should have an arrow there. I should never touch. So the domain for this function is actually all real numbers except x equals 3. X equals 0 gives me a point on the graph, but x equals 3 does not give me a point on the graph. Connect it back to the equation. If x is 3, you're going to subtract 3 and get 0. So x equals 3 is off limits. It's a restriction. So the domain goes from -infinity to +3, comma or union 3 to infinity. In studying the range, it's going to be the same as the parent function because I didn't shift this graph up or down. Okay, stop the video. If you feel comfortable, go ahead and sketch these out. Come back and look at the key. Example B. Okay, I'm going to shift this graph of the parent function left 1. So I'm going to take that asymptote at x equals 0 and I'm going to slide it to the left to -1. I might, just for the sake of my drawing, draw on this dashed line. Maybe I'll extend this and draw the graph like this. Let's state domain, let's state range. Well, the domain changes. I can have an x value of 0 because that won't contribute to my getting 0 down here. But if x is -1, then I am going to get a 0. So the restricted x value is -1. And the range didn't change because I didn't shift the graph up or down. All right, let's look at C and D. All right, notice that the placement of the +7 is not with the x. We only have x squared. So in this case, this is going to be a vertical shift, and this is going to be a vertical shift up 7. All right, so how do I handle that? Well, let's look back at the parent function. It was not mentioned when we studied this, but we do have a horizontal asymptote also. Not only do we have this vertical asymptote for the graph, but we have this horizontal asymptote. The branches of this graph will never touch y equals 0. So in fact and indeed, we do have a horizontal asymptote at y equals 0. So now let's jet back down here. So what does that mean if I'm going to shift the graph of the parent function up 7? Well, think in terms of this horizontal asymptote. Why don't we move that horizontal asymptote up 7? Because it's got to move too. So I'm just going to count off 7. And I'm going to put in a dashed horizontal line here to represent my horizontal asymptote at y equals 7. Now, I'm not shifting the graph of the parent function left or right, so my vertical asymptote is still going to be at x equals 0. So all I'm doing is just shifting the graph up. It's good to have this dashed line here, so it kind of gives you like a little stopping point so you don't go below it, and it looks nice and neat, and you can tell where the graph is. All right, let's see if we can report the domain and the range. All right. Well, it looks like the domain is like the domain of the parent function. I still can't have x to be 0 because then I would be dividing by 0. So we have the same domain as the parent function. It's the range that changes. What's the first y value that you're going to intersect? Well, it's above 7. So I don't want to include 7, and then I go up to infinity. All right, let's look at D. D is looking to be similar to C, except that we've got the constant first. So for me, I think it's helpful sometimes if I rearrange this and I see this as negative 1x squared and then the plus 3. All right, so it looks like it's going to be a shift up 3, but it's also going to be a reflection across the x-axis because of that negative 1, that multiplier there of negative 1. So we want to do the multiplication before we do the addition. So we want to do the reflection before the shift up, just like what you always do multiplication before addition. So what I might do is in a couple of steps here, draw this graph. So maybe I'll draw the reflection real lightly first. So if I take the parent function and reflect it through the x-axis, make it go upside down, it looks like this. But now I have to take this graph and shift it up 3. Okay, well, remember, we still have a horizontal asymptote at y equals 0, so why don't we move up that horizontal asymptote to y equals 3? So now the graph with the 2 transformations will look something like this. Good enough sketch? Let's see if we can record the domain and range. Well, the domain is all reals but 0. And the range is going to be negative infinity up to, now I have a cap on my answer, negative infinity up to 3, but we don't want to include 3. All right, let's take a look at E. All right, actually, I kind of threw you a curveball here. This is a non-example, okay, for this parent function. Okay, we're not going to shift the graph up, down, left, right, 6. This doesn't have the same structure, the right structure, in order to do a transformation. If I wanted to shift this graph down 6, then the equation would have to look like this. If I wanted to shift the parent function graph up 6, I would have to have a plus 6 here. Notice that if I want to go left or right, that minus 6 needs to be inside of parentheses. So sometimes it's good to look at a non-example to realize, hey, I can't use my transformational graphing to graph this because it doesn't fit the structure of this parent function. All right, take a look at F and kind of think about, oh, what's different here compared to all the ones that we did do? I hope you see that 10 on top. So what effect does that 10 have on anything? Well, actually, it's a vertical stretch. Okay, so let's just imagine that it was a 1 in the numerator. Well, that tells me I'm going to shift the graph right 6. So let me think about the parent function, which has togetherness at x equals 0. Let me move over 6. to move that togetherness to the right. Okay, now this 10 is actually going to stretch your graph. Okay, it's going to stretch it away from the axes. So what it does is it just takes a little longer to get to this vertical axis, asymptote, and this horizontal asymptote. I might have said axis earlier, I meant asymptotes. Okay, so it just takes a little bit longer to get there. It's a little further away. Okay, but that's not going to change your domain and range, that vertical stretch. All right, so for part of this assignment, I want you guys to go ahead and finish down here, 1, 2, and 3. This is your turn. Draw graphs for each of these functions, and then report the domain and range. And this is what you're going to take a picture of, the notes that we did together, and then make sure I see these down here so I can grade them. Let's look at our second parent function that's new to us. Okay, get a calculator. I want you guys to go to your calculator. Go to y equals, build a fraction bar, okay, and then in the numerator put the absolute value. I think there's a shortcut. I don't have my calculator in front of me, but I think there's a shortcut key for the absolute value. It might be under the green alpha button and then one of the function menus up at the top. Or you can always go to math and over to number. All right, so graph that and then record that graph over here in this space. Okay, when you graph something on a calculator, it doesn't reveal all the little details, but we're going to find out here soon enough that up here at 1 and down here at -1 on the x-axis, we have 2 open circles. We can't see them on a calculator, but we will know that after we complete these tables. And the graph is actually just going horizontally to the right, staying up here at a height of 1. All these y values are 1. And then over here to the left, okay, these y values are -1. So when x is greater than 0, my y's are 1. And when x is a value less than 0, my y's are -1. All right, we're going to build some tables here. Before we do that, I want to show you, this is also equivalent to having the absolute value around the x in the denominator, but not the numerator. However, this is not the same thing as having absolute value in both locations of the numerator and denominator. Okay, and actually this is just equal to +1 because this is the same number divided by itself. All right, let's build 2 t-charts, and what I want to do is I want to have some x values that are negative down here, and then in the second t-table, t-chart, I want to put just positive x values. Now to save time, I should have had this already here. I'll start at 0. I'll count off by half until I run out of spots. Okay, so again, it doesn't matter which of these 2 equations I use right here. So let's go ahead and plug in -3 for x here and -3 here. So maybe I'll show a few of them. So the absolute value of -3 over -3. Well, absolute value is going to take this negative number and make it positive. So now we're going to get +3 divided by -3, and we know that's -1. Double check it with your graph. Let's say that x equals -3 is over here. Well, yes, the y value, the answer, is -1. Okay, let's put in another value. So let me plug in -2.5 for both x's, one with absolute value and then one without in the denominator. Think about what's always going to happen here. This is going to be made positive, but you're still dividing by a negative number. You're dividing opposites, so this answer is also -1. As is this, 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 this. When you plug in 0, you're going to end up with 0 over 0, and that's what we call indeterminate, but the functional value is undefined. Let's plug in some positive numbers. Undefined here, All right, let's plug in 0.5. So I got a little space here. Got the absolute value of already a positive number divided by the same positive number. The absolute value bars have no effect on anything. I can just like remove them. I'm taking a number, dividing it by itself, and so that's going to equal 1. Plug in 1 here, 1 here. 1's already positive. 1 divided by 1 is 1. All of these are going to be positive 1s. So think about these x values that would be found and located over here, and all the answers that come out, except for x equals 0, of course, is 1. So let's state the domain. Well, the only x value that causes a problem and makes this graph discontinuous at this jump discontinuity, okay, is x equals 0. Okay. We call this a jump discontinuity because all of a sudden, abruptly, we have to jump from a y value of -1 to a y value of 1. We call the other discontinuity at x equals 0, we call this an infinite discontinuity. We have no jump here. It's just we have a vertical asymptote, so the graph continues to infinity, so we call this an infinite discontinuity, whereas this is a jump discontinuity. Kind of getting ready for another lesson coming up. All right, what's the range? Well, the only y values I see on this graph are that you're going to have y values of -1 or 1. So we want to be careful and not put brackets or parentheses around this. If you put parentheses, it's saying everything between y equals -1 and y equals +1. Brackets are kind of the same thing too. So what we usually do is just kind of use little braces here. And that just means that whatever falls between these braces, those are just finite answers. These are the only answers. We look at this as -1, 1, as it should be looked at. Ready? All right, what about A? Okay, what if we had the equation that looked like this, or if we drop the absolute value down here, based on what we saw up here with our new parent function that we should memorize. Okay, transformationally speaking, I see the same expression between the absolute value bars as what's down here in the denominator, x minus 1. So I really focus and hone in on x minus 1. Well, how does x minus 1 compare to x? Well, I'm between the absolute value bars, so I'm going to say, you know what? I think I have to move this graph to the right one value. All right, so let me kind of put my mind around that. So how am I going to move this graph to the right one value? Well, I have to move this part of the graph to the right and this part of the graph to the right. So the x value where we have a discontinuity is when x is 1, because that makes us have 0 over 0. So I'm going to go to x equals 1, but now remember this graph, okay, has answers of 1 and -1. So I'm not going to put the open circles here. I'm going to put the open circles lined up above and below x equals 1 when they're across from y equals 1 and y equals -1. So you're shifting both those. And in fact, you're just shifting both of those open circles to the right. So, and then all we have to do is draw off that circle to the right and this open circle to the left. So what's the domain? Well, all x's except for when x is 1, because that causes a problem. And the range didn't change. We use braces again, so we don't include everything in between. All right. So think about B. If you thought, oh, that looks like it's going to be a shift left 2, you're exactly right. So think back to the parent function. Think about taking both these open circles and shifting them left 2. So go ahead and get your marker here. Get a marker here, and a marker here. And remember, this is 1, and this is -1. To the right off of the top circle, and to the left off the bottom circle. And domain and range here as well. All right, looks like x equals -2 would cause the issue, so we want to exclude that and restrict -2. So -infinity to -2, etc. And same range. Okay, like the last example, I want to give you, like the last parent function, sorry, I want to give you a non-example. So look what I said here, not y equals ... or y equals this right here. So think about why this would not be fitting the pattern of this parent function to where I could do transformations. I won't ever give you a problem like this where you have to graph it unless you have a calculator, because you can simply put that in the calculator, and I'm not sure what it looks like, but it doesn't fit the description of this parent function because you have to have the same expression on top as bottom. It's just that either the numerator or denominator have to have the absolute value. So this is x minus 1 and that's x plus 1. So I certainly can't use my transformational graphing background to graph that. And the same thing here. That absolute value needs to be wrapped around the entire numerator, not just the x. So these are non-examples. Okay. All right, and then as part of your homework, now it's your turn. Okay, and I think I typed that up pretty quick, but they look good. Okay, sketch a graph of each of these functions. You can put them wherever you want, here and here, and then state the domain and range.